we want to see some examples of a vector field that is conservative and that is not. To find some conservative vector field, the easiest way is to write some potential, any function you like, with continuous derivatives. And if we compute the gradient, if we compute the partial derivatives, du with respect to x is 2x by cube, and derivative of u with respect to y is 3x squared y squared. Then if we take these two functions, these two expressions, as the components of the vector field, then this vector field is definitely conservative, and it has potential, which is this function u. It is easy to see, once again, to test the condition that this is indeed potential, this is indeed conservative. If we compute the partial derivative of the first component with respect to the second variable, then differentiating this, 2 is constant, x is constant, and x cubed derivative is 3, y cubed derivative is 3y squared. So we have 2x times 3y squared. And when we differentiate the second component with respect to the first variable, then 3x squared is constant and derivative, second with respect to first. So we have 3, x squared is 2x, and y squared is constant. And this is 6xy squared, 6xy squared, the same. So this is an example of a conservative vector field, and this is its potential. And now, well, yeah, perhaps what would be the simplest vector field which is conservative? The simplest vector field. The simplest vector field, what do you think? Yes, 0, 0. First, does it satisfy that these derivatives are equal? If we compute the first derivative with respect to x, 0. If we differentiate f2, first with respect to y, still 0. And second with respect to the first one, still 0. Yes, they are equal. And what is the potential? Which function has the property that its gradient is 0? Yeah, any constant function. U is a constant. Because then its gradient, that means the vector of partial derivatives, is equal to 0 and 0. If we think of the gravitational field, then 0 gravitational field corresponds to the state of weightlessness, something that experience astronauts when traveling in some spacecraft on the orbit of the Earth. Okay, and now, yeah, perhaps we can still find next almost simplest vector field. What if the vector field is constant? Say 5, 6. Then the derivatives are still 0, so the test says yes, it should have potential. And we can guess the potential. We want a function such that its derivative with respect to x is 5, so it looks like 5x. But then the derivative with respect to y should be 6, which is not the case here. But if we add 6y, then we are done. So the constant vector field is conservative, and it is easy to find the potential. And now what about the simplest vector field in the world which has not a potential, which is not conservative? Stop me for a moment and think it over. Try to find the simplest vector field which is not conservative, for which this is different. Stop me for a moment. Yeah? You found? So it should be non-zero, right? To be different. So take 1. F1 differentiated with respect to y should be 1. So this might be y. Then and we want this to be different from the derivative of f2 with respect to x. But this may still be 0, so no problem. f2 is 0, and then derivative of f2 with respect to x is 0. And they differ, so no vector field. Perhaps a candidate to the simplest vector field, which is not conservative, might be 0 and the second component, yeah, you got it? X. Because then the derivative of first with respect to y is 0, while the derivative of the second component with respect to x is 1, and they differ. This is a surprising situation, isn't it? If we go back to one-dimensional case, if you have some function and you add the differential, then this is always the differential of some function u. But if you have two expressions, f1 dx plus f2 dy, and you want this to be equal to the u. Sometimes it is the case, if you consider this function, then 2xy cubed plus 3x squared y squared is indeed the differential of u. That means the differential of the function x squared y cubed. Dx here and dy here. So it looks like if you take any expression multiplied by dx and add another expression multiplied by dy, it looks like this is a differential of some expression of some function. It is not. This is indeed the total differential of some function only in the case when this is equal to this one, which is quite a special condition. If you choose some function at random, then usually they will differ, the derivatives will differ. So some expressions, f1 dx plus f2 dy, some expressions are the total differential of some function, some are not. An example would be here or here. If you take this one, then y dx plus 0 dy is not a differential of any function u. And similarly, 0 dx plus x dy is not a total differential of any function u.